Hello everyone, and thank you for joining us for this webinar. The webinar today will cover eProtect, an enterprise protection and asset management solution. In this webinar, we will present the need, benefits, and demonstrate some of the key features of the ETAP Centralized Relay Database Management System, which is able to manage the lifecycle of protection relays and other substation assets all the way from design to operation. eProtect can be used in applications including transmission and distribution, mission critical, industrial facilities, railway power systems, and more. eProtect is a company-wide solution that offers benefits for ETAP engineers, operations and maintenance, reliability, IT, and compliance departments. So let's go ahead and get started. In this webinar, we will cover the key industry trends, challenges, and requirements. We will then provide a solution overview and demonstrate benefits of a centralized relay database management system that is leveraged off your existing ETAP model. Not only will you be able to find, share, track, update, and store asset data, but also optimize your network protection through an agile and flexible system which provides true insight into the big picture. We will explore industry landscape through its trends, requirements and obstacles, and how eProtect solution is able to overcome some of the challenges and provide instant value to the enterprise. As the hype around digital transformation continues to persist, the terms digitization and digitalization join the fray. This is a key concept behind eProtect. In reality, these three terms have distinct meanings, or at least we can make them distinct depending on which context we are applying them to. Digitization essentially refers to taking analog information and encoding it into zeros and ones so that computers can store, process, and transmit such information. Unlike digitization doesn't have a clear single definition. Digitalization is the use of digital technologies to change a business model and provide new revenue and value producing opportunities. Simply put, digital transformation initiatives will typically include several digitalization projects. We digitize information, we digitalize processes that make up operations of a business, and we digitally transform the business and its strategy. So each one is necessary but not sufficient for the next. And most importantly, digitization and digitalization are essentially about technology, but digital transformation is not. Digital transformation is all about the customer. All these needs, including improving reactive procedures, slow lagging health indicators, crew delays in restoring outages, unplanned downtime, grid failures, ineffective change management, etc., are ultimately impacting the customer, whether it be a consumer for a distribution company, a process unit in an industrial facility, a bulk system operator for a generation plant, and so on. Therefore, there are many reasons for an organization to embark on a digital transformation journey, and that always begins with digitization. And this is where we will begin as well. With a focus on greener power, improved efficiency, and the adoption of smart grid technologies, companies are upgrading from conventional substations to digital substations. Substations have undergone a gradual transformation over the past decade. The substation is regarded as a critical asset that needs to be managed in line with the organization's mission, which is a combination of customer, financial, and legal deliverables. Safety in the substation is at the forefront of all these deliverables. Asset performance needs closer monitoring as it impacts all key deliverables of the organization, whether it be financial, contractual, or regulatory. A digital substation is part of the secondary system that includes all of the protection, control, measurement, condition monitoring, recording, and supervisory functions associated with the primary process. The utilization of modern multi-object relays and open standards such as IEC 61850 for device-to-device communications allows for functional consolidation, elimination of control and interlocking wires, and greatly improves the system performance while increasing both reliability and personnel safety. As we know, power system protection emerged at the beginning of the last century with the application of the first electromechanical overcurrent relay. Majority of the protection principles currently employed in the relays were developed within the first 3 decades of the last century, such as overcurrent, directional, distance, and differential protection. In the last century, from the emergence of protection to the end of the 1990s, the relay protection has undergone through a number of development stages thanks to digital transformation and digital substations, and migrating from electromechanical to semiconductor and subsequently to integrated circuit and microprocessor technologies. Today, microprocessor-based digital and numeric relays are replacing conventional relays in all areas of power system protection, and that's one of the industry trends. This migration has resulted in vast amount of data and growth in the number of parameters for digital relays. Another industry trend that we are seeing is the trend to digitize everything and place it in the cloud, whether it be pictures, documents, catalogs, drawings, etc. There is a trend towards converting all this information, whether it be CSV, CAD, Excel, text, MDB, paper, and place it into a single source of truth and create a digital twin. Digital twinning allows for accurate representation of the power system behavior and responsiveness under various conditions, such that improvements can be made as part of the digital transformation journey. We have discussed that digital transformation is nothing but a combination of digitization and digitalization projects. A simplification of digitalization is shown here, and an ETAP solution that offers digitalization is eProtect, which allows relay information to be kept in a central location rather than just an ETAP model, automatically retrieves relay information to simplify data collection, notifies when there isn't any management of change, and can also generate optimized settings from the ETAP software. This is all done without complex communication and built-in templates and mappings. And of course, we will see this in a lot more detail in this webinar. Another industry trend is towards complex engineering. Protective relays offer a number of functions, including measurements, such as phasor measurements, events and disturbance records, fault recording, and other equipment supervision. It is possible to combine the digital twin model with power system analysis, coordination studies, automatic protection and coordination evaluation, arc flash assessment, historical events, real-time operating data, and so much more to constantly iterate and optimize the electrical system for any given condition. This leads to great flexibility in terms of operating the system, but it comes at the price of complex engineering. For example, it is possible to read the fault signature from a relay, determine the fault type, location, and play it back into the analysis program to determine the as intended operation. You can then compare it with the as designed and as operated conditions to determine a measure of success for your protection scheme. Another industry trend is towards grid compliance. Protection system design usually considers two aspects of reliability: dependability and security. As the speed and complexity of operations continue to escalate, the ability to stay in compliance becomes directly determined by effective system-to-system communication between many departments. It's easier said than done if your operations are vast. When a protection system misoperation occurs, the resulting system performance will depend in part on the type of misoperation that occurs and the characteristics of the power system on which the protection system is applied. There's generally a trade-off between dependability and security. And of course, improving one typically degrades the other. So therefore, with the number of increasing regulatory requirements that are being imposed, particularly on utilities, it is important to have a relay protection simulation software tool with a central database that can assist with meeting these voluminous requirements and help utilities and industries understand the reliability of their system. Based on the NERC 2016 State of Reliability Report, it's easy to understand the various causes of misoperation by their cause code. And as we can see, 26% plus another 9% are due to incorrect setting, logic, design errors, as well as human errors. The compliance, auditing, and management system, therefore, should be able to set up, save, and store study parameters and intuitively rerun the same compliance study in the future that pertains to these or other local standards. The system should allow for viewing color-coded study results to easily identify areas of non-compliance that require remedy actions, easily maintain and store study data in a database, and therefore allowing you to compare study results over time and support deliverables and documentations to prepare compliance reports for all of these different PRC standards. Now that we've seen some of the industry trends that are driving the digitization and digital transformation of the industry, it's time to take a look at a few of the industry challenges which we'll be trying to overcome as part of the eProtect solution. The very first one is data volume. Typically in industrial systems, you can have thousands of protected devices, and utilities may have tens of thousands of protected devices across their substations. And the number of assets can range anywhere from tens of thousands to hundreds of thousands of actual assets in the network. When you look at each location and each device, you can essentially have various parameters such as relay settings, fault waveforms, relay testing data, maintenance records, security and access control, IED management and configuration data, and of course the health index of each and every asset in the network. And this is typically saved in multiple databases that is consumed by multiple departments such as planning, testing, operations, design, and even training. So therefore there's a lack of common information access and of course a change management system to manage this data across the board. Another industry challenge is time shortage. Time shortages are caused by the fact that the entire implementation needs to be done in parallel with your daily work. Some of the processes are manual, such as the process of retrieving settings file, which could be including eyeballing of relay settings, especially for electromechanical devices, which make the process slow, time-consuming, and error-prone. In a typical industrial plant, give or take, it may require up to 2 months for complete relay data collection, which essentially adds to the delay in the coordination study, and of course exposes the study to errors that may include transcribing errors or completely missing or skipping some of the protection settings or the protective functions that may need to be collected from the field. Another industry challenge is lack of integration. Typically when we do our protection analysis, we produce a settings report, but the settings report is not the same as a setting file. So there's time spent in converting the settings report into a setting file that can be essentially uploaded to the relay. And this is essentially prone to errors, it's time consuming, and requires double data entry. Further, the legacy systems, especially the asset inventory databases, are not well integrated with any other central asset management system. So therefore, there's a need to link the inventory with the required components that you determine as a result of the study. And finally, equipment testing is also handled as a separate silo and not integrated with a centralized database management system. Another industry challenge is non-integrated IT support. What that basically means is the business process or the workflow from the start to the end has a number of manual steps, a number of double entries, and of course is prone to errors. And there's no standardized change management or access permission control in this type of workflow. This is a typical workflow, and though it may not represent all the workflows that exist in the industry, this is perhaps one of the most siloed approach you can think of, where an event in the system causes a misoperation of a protected device. Here we can see that relay 1 operates first versus OCR 8. So therefore there's a need to change the setting and optimize this condition, and that might be triggered through a phone call or an email to an ETAP engineer who performs the study. They essentially go into a revision and they perform a coordination study where they improve the optimization of the protection settings, and they generate an optimal setting. Now, if you recall, the setting file is different from a setting report. So the optimal settings are then emailed through Excel or PDF to another individual who would essentially convert that manually into the relay software and generate a setting file, which is then downloaded to the laptop and then finally uploaded to the relay. A question to also ask here is that when the engineer performed the study, did he use the correct starting point to do this assessment and evaluation in the first place? So there's a lot of unknowns through this non-integrated business process or workflow. Here's another portrayal of the life cycle of the protected device settings, where the planning department can provide the initial settings, and then create the setting files. They will create a test file, test, and then the test is verified by a commissioning engineer who then updates the setting file and a new version is created. And this previous version or the initial version is converted into a history. So again, this process tends to be somewhat manual and involves a number of data entries, double entries, as well as passing of documentation that might be in Excel or other formats. Non-integrated IT support also involves communication with the devices. So a system that is managing all of this data and the workflows should be manufacturer agnostic, such that it supports in principle all devices regardless of the manufacturer, and hence provides a unifying interface for the management of settings from various vendors. It should also be possible in the system to organize additional documentation associated with the device and settings, including relay manuals, application guides, instrumentation diagrams, and setting calculations. Another industry challenge is management of change tracking, or essentially having audit logs. Critical assets should have their maintenance history linked and tracked. This is important for scheduling maintenance and reducing downtime or turnaround time. And also, if there's any change or unauthorized change made in the system, then there should be a notification generated alarming or notifying management or the engineering management group that an unauthorized change was made. Another industry challenge is non-validated data quality. There's essentially no management of the setting history based on the workflow we saw earlier. There's no formal structural relationship between the protection setting and testing management. And there's no verification and validation of relay operation with respect to the study simulation. In other words, did the relay really operate the way it was intended or designed to operate? So to essentially address the industry trends and also address the industry challenges, we developed eProtect, which is a centralized protection and asset management solution for design, engineering, maintenance, and operation of industrial and utility power systems. eProtect implementation begins with substations and power distribution centers and collecting the digital and analog information from these devices such as relays, transformers, circuit breakers, and so on, using sensor networks and hardware such as ETAP ICE RTUs, the existing relays in the network, DFRs, DDRs, PLCs, and so on. And this data is essentially collected using multi-protocols such as DNP3, Modbus 61850, or even OPC. And that information is then transferred over to the real-time platform that hosts the ETAP wide area management, protection and control applications. These applications include PMU applications or phasor measurement unit, automated fault analysis system, grid compliance management, remedial action systems, as well as eProtect. These systems provide model-driven intelligence. They have a built-in reporting engine. They provide alerts and notifications using rule-based process automation, leverage ETAP for predictive analysis, and provide a combined software and hardware solution for you to manage, protect, and control your system. Of course, in this webinar, we'll focus primarily on eProtect. eProtect communicates with the protection relays by essentially retrieving the as-found settings, which are then passed on to the design and analysis workstation. The engineer performs the electrical system study and the optimization and passes the as-optimized results back to eProtect, and it is essentially hosted and maintained inside the central database. And these settings can actually be sent back to the relay and overwritten without any double data entry or any transcribing errors, and have a full documentation of all the versioning that has happened from the as found to the as optimized settings. We can then also retrieve the waveforms or the fault waveforms from the relays, RTUs, DFRs, and store the events and the disturbance records inside eProtect and pass those to the design and analysis workstations for further investigation and forensic analysis. The fault waveform that is brought into the design and analysis workstations is then used for fault location. Once the exact or accurate fault location is determined, it is then sent back and saved in eProtect along with the event. So for every event and disturbance record, you know exactly where the fault was located with respect to the electrical model or the single line diagram or the geospatial representation of the electrical system. This fault location information can then also be sent over to ETAP OMS that is used for essentially crew dispatch as well as outage restoration. You can also send the sequence of operation to the design and analysis workstation, and using the fault that is simulated inside the program, you can then use the sequence of operation from the as operated system and compare it with the sequence of operation in the as designed or as intended system. And you can then determine whether your system protection schemes are operating effectively or not. All of this information is accessible through eProtect web clients that allow you to visualize and interact with the data using a web browser or a tablet. The design and analysis workstations allow you to perform network modeling and analysis that includes equipment modeling, power system analysis. They include GIS integration with asset tracking, and of course host the popular ETAP star and star Z protection and analysis modules. The eProtect database itself performs the asset lifecycle management by hosting the central relay database. It has standardized settings and process, as well as a substation hierarchical model that hosts relays, breakers, CTs, VTs, batteries, and of course relay settings themselves. The eProtect client is a web-based enterprise-wide secure access client that provides maintenance and operational support, health monitoring, and it's a window also into AFAS, PMU visualization, workforce management, and more. So let's take a look at some of these elements in action. First up is going to be web interface. We start off with ETAP that includes star and star Z protection analysis modules, the eProtect asset management system, and an optional connection to the ETAP real-time platform. The ETAP model, which is your existing single line diagram, can be augmented using ETAP app, and the data can be collected and collaborated with also using NetPM or Network Project Management. That includes the settings, one line diagram information, GIS information, and other asset information such as transformer impedances, grounding information, and other protection related data. That information is sent from ETAP network model to ETAP eProtect asset management system. So you can essentially hydrate your eProtect database by starting off with your ETAP electrical system model. This also includes network model updates such as incremental updates for your one-line diagram. Various functions such as change management, enterprise access and visibility, security permissions and access roles, settings change notification, and audit reports are all triggered and run within the eProtect enterprise. The window into eProtect is through our web-based dashboards such as GIS visualization, tabular dashboards, as well as the schematic one-line diagram. So let's take a look at some of these features inside eProtect.
We are now viewing ETAP Online, which provides a web-based visualization of our project, along with many of the key features of eProtect and information required to manage the system. Additional tools are provided for design and operation. This includes asset information, management with dashboards, trending views, and alarms. Additionally, from the web, we can also run analysis such as load flow. eProtect specific tools such as relay settings and the history of any changes applied. But now let's focus on the GIS system. We are showing the distribution system in a web-based GIS. ETAP GIS provides owners, operators, and planners geospatial tools to better analyze, design, operate, and expand their network. Display options allow us to select which sections of the system we want to visualize, including the primary distribution line, secondary distribution line, secondary distribution load line, which I am now showing. We can determine which devices we want to show, and since we are focusing on relay assets in this webinar, I'm displaying the relays and managing their locations. We can clearly see on the GIS where the relays are located. If you are integrating this system with the ETAP outage management, you can also visualize the location of maintenance vehicles, lightning strikes, and Twitter tags. From this GIS system, we can transition to a corresponding substation view to look at the details of the substation. This view gives us a plethora of additional options to manage the system, which Tanush will now highlight.
eProtect can also be used for visualizing asset health information, such as key performance indicators from ETAP ICE, ETAP Tesla dynamic distance recorders, and of course other IEDs and digital relays. Using direct multi-protocol communication, we can use the ETAP real-time platform for predictive analysis, maintenance history and archiving, generating KPIs, performing SCADA visualization, automation and control, and of course prescriptive analysis. The asset operation history can then be synchronized with the eProtect database as well as the asset maintenance schedule. However, the ETAP real-time platform is optional, so eProtect can communicate with all of these devices directly, allowing you to retrieve information such as fault waveforms and the relay settings directly from these devices.
Our substation SCADA view is graphically customizable, so users can configure the view to their preferences. Any details from the substation can be configured, brought in, mapped. The tags can be mapped over and monitored. Currently, we're looking at real power and reactive power associated with various meters on the network, as well as bus voltages. We are not limited to just these measurements. Any measurements available through the telemetry on the field can be displayed. You can also configure dashboards for specific components, and this can be used within the model. For example, this transformer, KPR3_33TFR1. This dashboard contains voltage levels, so we can see voltage from AB, BC, and CA, current levels for ABC, transformer information like temperature, latitude and longitude for location, and this even contains a trend view. In this case, it's real power, but this is also selectable as well, so anything you wish to trend you can create within this dashboard screen to specifically monitor any component that you choose. As ETAP is an intelligent SCADA, it detects configuration changes in the network, or if the operator simulates a breaker trip. So if we open this tiebreaker, even just to simulate, the configuration is detected and continuity check instantly shows when the breaker is open and parts of the system become de-energized. We are currently looking at the electrical network, but now let's look at the physical representation. The physical twin includes the representation of the panels as they are constructed, including nameplates. These faceplates contain real-time data, indicators, and you can also send commands from the nameplates, so you can open and close from this relay itself. These faceplates are templatized, so you can pull from an existing template or create a new one to use for a specific relay model. Then you just select the template per relay, and the real-time data and all indicators from that relay are based off the specific relay model. So in this case, we're looking at CHSD_MM. All the data correlates to that relay specifically, but if I go to VKP_MM, now the real-time measurements are specific to this relay. In addition to the relay faceplates, we have the relay health indicators. Various parameters from the relay are monitored that are critical to the life cycle of the relays. This allows us to see how the relay is behaving, as well as historical maintenance information. This page is customizable, so you can determine which fields to monitor for a health index. In this case, we are looking at certain conditions in red. Under communications, we see that a few relays are offline, so we can't communicate with these relays right now. Specific breakers are tripped. You can also see a trip counter for maintenance purposes. We see the last maintenance and test date, which allows us to properly forecast for any future maintenance plans. This alarm indicator shows the number of unacknowledged alarms we have. The initial list displays the last 5 most recent alarms with details such as timestamp, component name, measurement type, and a message. However, these details can be defined by the user. The alarms displayed are based on an area of responsibility, so you will only see alarms for your specified area. These alarms can also be emailed or texted to the appropriate personnel. In the alarm management system, I can view all the alarms for my area of responsibility and details of each one. Alarms can include communication loss, trip signals, health signals, power measurement thresholds, and disturbance files. Here we can see a waveform file received and as an alerted item. Once reviewed and confirmed, we can acknowledge or delete alarms. As I acknowledge these 2 alarms, you'll notice under the column are now set to true.
So let's see a quick demonstration of how eProtect is able to read and write settings. But first, conceptually, let's understand what is going to happen. A schedule setting retrieval or an audit report is triggered. This can be done on a scheduled basis or on a manual basis. eProtect then connects to the relays and is able to read the relay settings file. This is either through a direct interface to the relay using the multi-protocol support such as DNP3, 61850, or Modbus communication, and it's then able to download the setting file from the relay. The setting file is then parsed and then essentially is visualized inside the eProtect web-based interface. The setting file is also stored in the database and version controlled. The setting file is then broadcasted through NetPM and then downloaded into ETAP design and protection analysis software, where you can essentially visualize the TCC or the distance characteristic for the relay. A settings change notification may also be triggered if the ETAP coordination program has a setting different than what was just retrieved from that relay. So let's take a look at how eProtect is writing the setting file. It may be possible that using ETAP design protection analysis software, you may be changing the coordination settings in ETAP star or star Z. And one of the changes could be by just changing the time dial on a particular relay. Note that this is a setting change on a generic relay and not an exact change. However, ETAP knows that this relay 1 is a particular type of relay. So essentially by making this change, ETAP automatically generates the settings, sends it over NetPM, which then downloads it into the eProtect database. And that settings file is essentially visible across the enterprise. That triggers a change management workflow that goes through the security permissions and access roles of who can essentially further process those settings. A schedule setting retrieval and audit is essentially run, which is comparing the existing setting inside the eProtect database with the new settings that are coming in. And if there is an update on the settings that are arriving from ETAP versus those inside the eProtect database, then a notification is generated again, letting individuals know based on their security and permissions that a change has been updated or added to the eProtect database. The settings are then combined with the rest of the settings from that particular type of relay to create an overall setting file. And then that's visualized inside the eProtect web-based application. And then it is also possible to essentially create that setting file that you can put onto a laptop and upload to a relay, or use the relay software to update the relay settings, or even have a direct interface to the relay and write the settings for the relays that actually support this type of communication. So through a complete automated process, eProtect can read and write settings, including creating the setting files, without having to redo or rewrite any of that information again.
The Relay Explorer is the primary user interface for eProtect. This includes a list of all the relays in the system, which comes from the ETAP digital twin. The classification section allows us to filter and sort these relays based on various classifications, which is user-defined. We can select which details we would like to see in this view: street address, city, substation, and many more. We can export all of this information to Excel for deliverables or for any other purpose. Using the File Manager, we can import various technical files. I'm going to import, select an IEC 61850, and import a CID file. You can do this from an OEM file or from the relay itself, and store this in a centralized database. Selecting Relay 1 allows me to view all the settings of this relay. I can see the labels and description as provided by the vendor. There is also a filter for ETAP that I can set to true, which filters the properties to the ones that is used by ETAP for protection and coordination studies. The version manager compares different settings from different time periods, and I can compare and see the overcurrent pickup was changed. Historical settings are stored and can be pulled to view in the main table. So I can select which one I want, hit display, and my table is updated with historical information. And the relay settings can also be exported to Excel directly from eProtect. eProtect combines a centralized protection asset management system with protection and coordination study results to manage information, optimize settings throughout the lifecycle of the relays and substation assets. We are going to download the settings file, send them to ETAP, and use Star Auto to automatically evaluate the protection settings. First, select which relay we're going to import the settings. These settings come from the actual device through the OEM software or can be configured to come directly from the relay. Once uploaded, you'll see that the latest sync time has been updated. All the settings are now displayed, and you can see the details of all the parameters for this specific relay. Next, we are going to send these settings to the ETAP digital twin. The comparison report shows the difference between the settings in the current ETAP model and what we are sending through eProtect. We are changing the pickup from 3.2 to 2.06 and the time dial from 0.09 to 0.23. The ETAP model is automatically updated. However, this data is sent to an eProtect revision, not the base revision, so you do not overwrite your base conditions. Relay 1 shows the updated pickup and time dial for this revision, 2.06 and 0.23. Now we can do a protection study with these settings and use Star Auto to automatically evaluate the protection settings. Star Auto tells me that I have errors based on the long time pickup value, which is below the minimum limit of 433 amps, which is based off of base FLA times 100%. These guidelines are set in the Star Auto rulebook. I can adjust the settings directly from the TCC view within Star Auto. Once I adjust the settings, Star Auto instantly updates to show me that all my protection settings are within limits. Now I can take my eProtect revision, use the data manager to take a look at the details of the differences. So when I select properties, I see the difference from 3.2 to 2.1 in my base case. And since we've updated this through a protection study, I can now drag it, override it to base, and update my base model with my eProtect settings. This instantly updates the eProtect database with the new settings from my ETAP digital twin. From there, I can either send to the device directly or export to a vendor file and save this information in the updated vendor file.
Now that we've seen the retrieval and writing of relay settings in action, let's take a look at the settings history and auditing function. This may be a typical workflow, but again, not the only one, where the substation relay information is retrieved, and that is essentially indicated as found setting in the workflow. You can then create a diff or difference against the as designed, which is essentially coming from the ETAP design and analysis database. You can of course then go to ETAP and create an as optimized settings. So again, we can see that there are actually two versions that are kept at this stage, including the as found settings themselves. Another version can be created where you're doing a diff against the as designed versus optimized. For those of you who use ETAP would know that the as designed is usually kept in base revision and as optimized could be kept in another revision. And we're essentially doing a difference against the base versus revision versus the settings that are being retrieved from the eProtect database. You can then create an as optimized setting file, which is then created based on the optimized settings that are merged into base. So this as optimized setting file can then be updated into the actual relay, and this is essentially known as the updated as found or the new version of the as found. And this is another version that can be differentiated against the previous or the historical as found setting. So essentially different versions are retained on the ETAP software analysis side as well as the eProtect database, and they can essentially be compared at any point with respect to each other. So let's take a look at setting history and auditing in action.
With changes to the settings from different individuals, it is vital to audit the changes done to these critical assets. All actions are automatically audited through settings history in a centralized database. All attribute changes are recorded, including downloads, uploads, as well as any other action taken. It is all audited and tracked in eProtect. You can also see who made the change and when under user and timestamp, but these columns are fully customizable by the user as well. So you can add or decide which columns you'd want to incorporate for audit management. All the actions we recently performed were recorded. We can see when we downloaded the relay settings files from the OEM software, sent the as-is settings to ETAP, and then received the optimized settings back in eProtect. The columns are customizable and each can be filtered to acquire any information necessary to audit asset management. So if we wanted to filter by the most recent work we did for Relay 1, we can filter by the relay name, and we can also filter by the subcategory. This allows me to see how often these settings have been changed from an ETAP protection and coordination study, as one example. But you can select from many different subcategories to filter out and manage the changes that have been done to the assets on the field.
Now that we've seen settings history and auditing in action, let's take a look at fault waveforms and how eProtect handles this type of information. Protection relays and DFRs not only send their individual settings and configurations, but they can also send waveform data such as phasor and instantaneous information using C37.118 or C37.111 and other formats. This information is sent to many different applications, including AFAS, which is Automated Fault Analysis System. But first, it's actually saved inside the eProtect central database as an event and disturbance record that you can actually visualize and do some detailed forensic analysis on the waveform itself, along with various signal processing. Within AFAS, the signal processing includes fault detection. So essentially to look at a waveform and understand whether there's an actual fault or some other type of disturbance in the network. Fault type identification, such as the fault type, whether it's face-to-face, face-to-ground, and so on. The fault location, or essentially the fault distance, in case the relay does not provide the fault distance information, but more particularly to visualize that fault location graphically on the network model or the geospatial model. And once the fault location is visualized, you can then do the as operated versus as designed. In fact, the fault waveforms that are visualized in eProtect and saved can also be used for grid code compliance as well as remedial action schemes. And the RAS or remedial action schemes particularly use the phasor or PMU data for that purpose. So let's take a quick look at fault waveforms in action and how they are visualized and stored within eProtect.
Through eProtect, we can visualize any recorded waveform. Selecting the recorded event by component, we can view the details of the measurements captured. All the available measurements that are recorded are filtered under the device. Selecting phase B, current, shows us the captured waveform, and the chart shows the values at any selected point on the plot. You can clearly see the event that occurred and the instantaneous results of that event. Select any measurement you wish to view and a plot will be displayed. For a more detailed look into the waveform, we can use the Waveform Viewer. The Waveform Viewer allows us to add plots of different calculated results for each signal. The signal types are listed, including instantaneous that we previously viewed, RMS, which ETAP calculates, as well as other results such as frequency, harmonics, power, and even user-defined plots that were previously created. We can select to show instantaneous as well as RMS, and the measurements can be combined into a single plot or viewed individually.
Now that we've seen how eProtect interacts with fault waveforms and is able to visualize and store the disturbance records, let's quickly summarize the features of eProtect, which is a scalable and modular system. It provides notification alerts for unauthorized changes. It's a simplified enterprise solution with web-based thin client interface. It provides high security standards and encrypted data transfer. It has the largest expandable verification and validation library, as well as customizable reports. Includes work order and change management workflows. It's integrated with ETAP planning, design and analysis software, and is able to also give you asset health tracking, management, and notifications. And finally, it also allows for management of change as well as audit trails. And finally, what makes eProtect solution stand out in the industry today is its ability to use an unstructured and flexible database. So this unstructured database allows for maximum flexibility when you're storing any relay or asset data set, because as we know, we can go from one asset to another and increase the number of parameters or properties of that asset by 2 to 3 times. And this essentially requires a database structure that is not so rigid and can accommodate any new device types or even new devices from different vendors. eProtect also includes engineering libraries that are verified and validated under ETAP Nuclear QA. These libraries are of course user customizable, and we also offer expandable adapters that can communicate with other relay vendors that we may not have in our current library. The ability to have these expandable adapters gives us the capability to perform direct communication, which means we are able to read and write setting files and process them directly and in many cases without using the relay software. The intent is not to bypass the relay software, but to improve the efficiency of reading and writing the settings and not necessarily change all the other parameters that the relay vendor software offers. And finally, the eProtect solution is integrated with ETAP technologies such as Star, StarZ, Star Auto and ArcFlash Auto, NetPM for project management, ETAP app for field data collection, and the real-time platform that includes AFAS, wide area monitoring, protection and control, remedial action schemes, and a whole lot more. We thank you once again for attending this webinar, and we look forward to seeing you in the future webinars. Thank you.